Hello, this is 54M, and today we're talking about using memory to store fractions. When we store fractions in decimal, we use a decimal point to signify that everything to the right of the decimal point is representing a part of a number. And what we want to do when we're storing fractions in binary is something very, very similar. The problem we have is that we only have ones and zeros to play with when we're using binary, so there's no easy way to specify where the decimal point actually is in the number. The other difficulty is that if we have a really small fraction, such as 0.00003, we only have one significant digit, the 3, but this is consuming a lot of space to store this very small number with only a single significant digit. To overcome these problems, we're going to take some inspiration from scientific notation. Scientific notation is used in scientific fields to represent numbers of all magnitude with a fixed number of digits. And the way scientific notation does this is by allowing us to slide this decimal point back and forward by adjusting the power to which we raise this base number. We can break down the scientific notation into a few constituent parts. The significand is the signed number. It's the meat of the resulting number or fraction. We also have a base. This is the number raised to some power. And we also have an exponent. This is the power itself, the scaling magnitude. It is the exponent which determines the scale or the size of the resulting number. We can also add a couple of hacks here to make it even easier to store this scientific notation type format in memory. The base is going to be invariant. Once we agree it up front, we aren't going to change it. That means that as long as the program knows what the base is, we don't actually need to store the base in memory. We can just use the same base for all numbers which we store as fractions in the future. Similarly, we don't need to actually store the decimal point. Just as we do with scientific notation, we can always assume that the decimal point comes after the first digit in the scientific notation. This means we don't need to worry about storing it within the binary number, and it also means that we can slide that decimal point up and down without actually needing to worry about adjusting where it's actually stored. So if this is our scientific notation for the number 0.0042, we know that in this case we're going to pre-agree the base is 10 decimal and it won't change. As long as the program knows that the base is 10, we don't need to store it. This leaves us with the exponent and the significand. We're going to assume that the decimal point always comes after the first character, so we don't even need to store that. This means that in memory we can store just two numbers. The number 42, which is the stored significand, which is actually representing the number 4.2, but we don't need to write the decimal point, and the exponent, which in this case is -3. And this is all the information we need to store the decimal 0.0042. We know the base is 10, so we don't need to store that. The program will know it when it comes to apply the notation. We know there is an invisible decimal point after the first digit, in this case after the 4. And given all of this, we can recompose the decimal which we were storing with just two numbers. This method of representing fractions is called floating point specification, quite obviously because by simply adjusting the exponent we can float that decimal point up and down without ever actually having to store it or represent it in binary in any way. So we've seen how this works in decimal, so now down to the exciting stuff of figuring out how we actually do this in binary on the computer. Let's take another example. In this case we want to represent the decimal number 4.25. How would we go about doing that? Well, first of all, no surprise. Inside the computer we don't want to use base 10, we're going to use base 2 because we've built an understanding of how we can use computers to perform operations on binary representations. That is base 2. We aren't going to abandon that now. Because we're working in binary, it will be easier to convert the desired fraction into binary too, so that we make things easier to work on. So 4.25 in binary is represented 100.0 0, 1. This makes it quite easy to find our binary significand now. We simply take the digits from the resulting decimal, ignoring the decimal point, which of course is going to be assumed, and we can write it just like this. Here we're writing the point after the first digit in the significand, but when we store this in memory, we won't be storing the point at all. It will be assumed to be after that first digit. Now we can finally and quite easily figure out the exponent. This is how many places to the right do we need to move the decimal place. In this case, we need to move the point 2 places to the right. In binary, that's written 1, 0. So this is our scientific notation, written all in binary base, representing the decimal number 4.25. So remember, the base doesn't need to be stored as it's pre-agreed as part of our standard. In this case, we're using binary base 2. And we can't store the decimal place, so of course it's going to be implied during storage as being after the first digit. Now we can store this in memory, and we can use a single byte to do it. If we to set aside 6 bits for the significand and 2 bits for the exponent, we're able to store this fraction in memory in a single byte. And in memory, that byte is going to look something like this. The first 6 digits representing the significand and the final 2 representing the exponent. Again, as long as the program knows which bits represent the significand, which bits represent the exponent, and what base we're using, it's able to work backward to figure out what the decimal actually is. When our program comes to read this, it knows to take the final 2 bits, use that as the exponent, raise it to the power we already know we're using, in this case 2, and then, once we have that answer, multiply it by the significand with the implied decimal point after the first bit. And by performing this operation, we're able to derive the fraction we originally stored using just 1 byte of data. Now this operation to derive the original fraction might seem a little cumbersome, and to be honest, it is, but it gives us the huge advantage of being able to store numbers of any size and any magnitude with a fixed number of bits. Now, if we amped up our specification a little bit to use 2 or 4 bytes instead of just 1, this will enable us to store numbers of a great range of magnitudes. In fact, using just 4 bytes, floating point notation is able to represent numbers as small as the width of a single cell and the distance between here and the Andromeda galaxy. And that's all using a fixed width, a fixed number of bytes, by focusing specifically on the significant digits in those numbers. And of course, with the enormous flexibility of using the exponent to slide that decimal point back and forward as we need to. But of course, there's something we've skipped here, which is that in the first example we looked at, where we stored 0.0042, we had to use a negative exponent in order to get that very small number. But in our binary example, we used a positive exponent. So how would we actually represent a negative exponent in order to get these very small numbers? If you saw the last video, you'll know that we can represent negative numbers using 2's complement. But 2's complement is actually more than we need here. 2's complement is excellent because it allows us to add negative and positive numbers. But in this case, we don't need to do that. With the exponent, all we need is to derive as quickly as possible and as easily as possible the positive or negative number that we need for the exponent. In order to do that in an easy way, we instead use what's called a biased range. A biased range of numbers is a range where we apply some bias to each number in the range to shift the range that is actually represented by those numbers. This allows us to use an all positive or absolute range to represent part negative and part positive numbers. In this example, we have a 3-bit exponent in the left-hand column. 3 bits is handy just for example's sake. With 3 bits, we can represent the range 0 to 7. We can give our range a bias, where the bias is the largest number we can represent plus 1 halved. In this case, the largest number we can represent is 7, So plus 1 halved is 4. This means that each number actually represents the number 4 less than itself. So, for example, when we store the exponent 0, 1, 1 in memory, we're actually representing the number -1, because that's 3 minus 4. And you can see in this right-hand column, for each binary number minus the bias that we've chosen, the actual number that it represents. And you can see that this all positive range is now able to represent a part negative, part positive range. This allows us to store exponents which are both negative and positive without needing to worry about flipping bits or anything more complicated. This is a quick and simple way to store negative numbers, which allows us to derive the negative number with a simple subtraction. This allows us to very quickly get to the number that we need for the exponent so that we know how many places we need to shift the decimal point. And the importance of being able to store negative exponents as well as positive exponents is that it gives us the freedom to represent very small and very large numbers using the same range of exponents. And of course, the number of bits reserved for the exponent defines the size of the exponent, negative or positive, and therefore the range of numbers, fractions at the small end and very large numbers at the other end, that we are able to represent with our floating point specification. The larger the exponent can get, this means the smaller numbers we can represent and the larger numbers become that we can represent. But as always, there is more than size at stake. The significand defines how precise we can get in representing our fractions and our larger numbers too. The size of the significand determines how close, how precise we can get to the number we actually want to represent. Given that the significand represents all of the significant bits in our resulting number, whether it be large or small, the size of the significand is vitally important for determining the precision of the resulting number. And if our significand is only 4 bits long, for example, there is absolutely no way that we can represent a number with 5 significant bits to complete precision. In this example, we cannot represent the decimal 0.0011001 with a 4-bit significand to complete precision, because it has 5 significant bits. And our problems don't end there, because it turns out the base is actually quite an important factor as well. To understand this, it's easiest to consider things in decimal, our natural number system, and the limitations that exist in the decimal system. Given only finite space, which for now is the only space we have to work in, it is impossible to represent to complete precision the number 1/3 in decimal. In decimal, we have to write 0.3333 recurring, because this never ends. In finite space, in decimal, we are unable to represent 1/3. But why? The verbose answer is that for any base, we can only represent those fractions which have denominators that can be composed solely of multiplication of the prime factors of that base. What does that actually mean? Well, 10 has the prime factors 2 and 5. This means that we can only represent fractions in base 10, where the denominator can be formed from these 2 factors alone. In base 10, that means that we can represent any fraction where the denominator can be formed using only the factors 2 and 5. For example, in base 10, we have no problem representing a half as 0.5 because the denominator 2 is a prime factor of 10. And equally, we can represent 1/4 because 1/4, 0.25, has the denominator 4, which is 2 times 2. Again, we're only using the prime factors of 10. And the same with a fifth and 1/10. 1/10 is 5 times 2. That is both the prime factors of 10, so we can easily represent that 0.1 in decimal. But we cannot represent 1/3, for example, because 1/3 cannot be composed from the factors 2 and 5, and the same is true with 1/7. Therefore, both of these fractions cannot be represented to absolute precision in decimal. It's important to remind yourself here the denominator must be formed only of the base's prime factors. So although 6 has the prime factor 2 in common with base 10, we cannot form it using only 2 and 5, because only 2 times 3 gives us 6, and 3 is not a factor of 10. So that's things in decimal, but things get even worse using base 2 binary, because binary 2 has just one prime factor, which is 2 itself. So using binary, base 2, we can only represent fractions where the denominator is a power of 2. That means halves, quarters, eighths and sixteenths are great, but fifths and tenths are absolutely out in binary. They can't be represented completely precisely. For example, 1/5 in binary is a recurring fraction which looks something like this. There are some tricks which some floating point specifications can choose to get a little more precise, but none can promise absolute precision on all fractions. As a result, we have to round these recurring fractions. And rounding means inaccuracies and, as a result, errors. As an example, pick your favourite programming language. Type in 0.1 plus 0.2. I guarantee you the answer will not be 0.3. You've just experienced a floating point error, because binary cannot accurately or precisely represent 0.1 or 0.2, a fifth and a tenth, using our floating point specification in binary. So these numbers are being rounded, and it is the rounding errors that you are seeing when you are adding 0.1 and 0.2 to get some other slightly off answer. And that is the imperfect science of storing fractions in binary. There are, of course, other ways of storing fractions in computers, which could be the topic of another video, but floating point numbers are the fundamental method used by computers for decades now in order to store decimals. And that marks the end of this mini-series on storing primitive data types in memory using binary representations. In high-level programming languages, of course we can store more complex data structures in memory, but these structures are just abstractions on top of these very few primitive data structures that we've discussed in the past videos. And the key to understanding those more complex data structures is in getting a grip on these primitive data structures and how they're represented in binary. This is 54M. Thank you for watching.